And welcome again to another Astronomy Daily. It's the 14th of July, 2025.
Astronomy Daily, the podcast, with your host, Steve Dunkley.
Wow, the 14th of July already. It's as close to the halfway mark of the year as we can get, Hallie.
I think you watch that calendar a bit too closely, human.
Oh, Hallie, it's just a way of marking time. You know, humans like to do that. I guess that's where our fascination with astronomy came from in the first place.
That makes sense.
Yeah.
Speaking of time, it's great to be back in the Australia studio again for this podcast time.
That's right, Monday is our time.
Have you got our schedule set up?
What? Yeah.
It was your turn.
Well, yes, Hallie, I got it done in time.
That's good. I hope it didn't take too much of your private time.
Oh, private time? No, not this time. As if I had any private time.
So, what have you got for us this time?
Well, Hallie, it's time for another meteor shower, and Australia looks like it's in the prime location for the best view.
It's about time.
Well, I suspect Australia is always in the best position for a meteor shower, so, well, viewing anyway.
Okay. What else?
Well, as the Perseids, we've got building things on Mars with fungus. Astronomers looking at the cosmic web, and we might actually be living in a giant void. They sound pretty cool, don't they?
Excellent. Okay.
So, hey, Hallie.
Yes, human.
How's about we just launch right into the episode?
And save some time, you think?
Tempus fugit, Hallie.
Indeed, it does.
Okay, Hallie, you have the con.
Okies. One of the main objectives of the Hubble Space Telescope, launched in 1990, was to measure the size and age of the universe, as well as the rate at which it is expanding, aka the Hubble constant. This was enabled for the first time with the Hubble Deep Fields, which visualized the farthest galaxies that are observable in visible light, 13 billion light-years from Earth. However, when astronomers measured the distance to these galaxies, they noted a problem: they were inconsistent with measurements of the local universe. This became known as the Hubble tension, which remains one of the biggest cosmological mysteries to this day. While astronomers hope to resolve this tension with the launch of the James Webb Space Telescope, Webb's measurements confirmed what Hubble saw. Many theories have been advanced to explain this, including the possibility that the Milky Way is located inside a giant void that makes the cosmos expand faster here than in neighboring regions of the universe. The latest research supporting this theory was presented at the Royal Astronomical Society's National Astronomy meeting in Durham. Their theory could potentially resolve the Hubble tension and confirm the true age of our universe, which is thought to be about 13.8 billion years old. The Hubble constant takes its name from Edwin Hubble, one of two astronomers, the other being Georges Lemaitre, who confirmed in the early 20th century that the universe was in a state of expansion. This was demonstrated using redshift measurements, where the wavelength of light from objects receding from Earth is shifted toward the red end of the spectrum. Before the Hubble Space Telescope was launched, astronomers were able to gauge the distance of objects up to 4 billion light-years away using a combination of redshift and parallax measurements. The problem was that when comparing local measurements to those of the distant, early universe based on the standard lambda cold dark matter cosmological model, the results were in tension with each other. The latest research, explained Dr. Indranil Banik of the University of Portsmouth, shows that Baryon acoustic oscillations, BAOs, essentially the sound waves of the Big Bang, support the idea that our galaxy could be in a void where cosmic expansion is greater than the universe beyond. Banik said, a potential solution to this inconsistency is that our galaxy is close to the center of a large, local void. It would cause matter to be pulled by gravity towards the higher density exterior of the void, leading to the void becoming emptier with time. As the void is emptying out, the velocity of objects away from us would be larger than if the void were not there. This therefore gives the appearance of a faster local expansion rate. The Hubble tension is largely a local phenomenon, with little evidence that the expansion rate disagrees with expectations in the standard cosmology further back in time. So a local solution like a local void is a promising way to go about solving the problem. This void would need to measure 1 billion light-years in radius and have a density roughly 20% lower than the average for the universe as a whole. This theory is supported by a direct count of local galaxies in our cosmic neighborhood since the number density is lower than in neighboring regions. However, the existence of such a void is inconsistent with the LCDM model, which includes the theory that the universe is antistropic in nature, meaning that matter is uniformly spread throughout the universe on large scales. Despite this, the new data presented at NAM 2025 indicates otherwise, said Bannock. These sound waves traveled for only a short while before becoming frozen in place once the universe cooled enough for neutral atoms to form. They act as a standard ruler, whose angular size we can use to chart the cosmic expansion history. A local void slightly distorts the relation between the BAO angular scale and the redshift, because the velocities induced by a local void and its gravitational effect slightly increase the redshift on top of that due to cosmic expansion. By considering all available BAO measurements over the last 20 years, we showed that a void model is about 100 million times more likely than a void-free model with parameters designed to fit the CMB observations taken by the Planck satellite, the so-called homogeneous Planck cosmology. To confirm this theory, researchers must compare the local void theory with other models to obtain new estimates for the expansion history of the universe. This will consist of obtaining spectra from quiescent or dead galaxies, those no longer forming new stars, to determine what types of stars they have and in what proportion. Since massive stars have short lifespans and are absent from older galaxies, this will help astronomers establish the age of these galaxies. Combined with a galaxy's redshift, astronomers can chart the history of cosmic expansion.
You're listening to Astronomy Daily, the podcast with Steve Dunkley.
Landing on Mars once felt like a distant dream. Now space agencies have sent rovers and landers to explore the red planet for decades. Scientists worldwide are thinking about how to make Mars a second home for humans, but major questions still remain. How do you build structures millions of miles from Earth? Shipping heavy loads of materials to Mars from Earth is expensive and impractical. Rockets have limited space and fuel, and sending cement and metal beams would cost billions. Researchers are now exploring ways to use what Mars already has, its soil, dust and natural resources, to build homes for future astronauts. At Texas A&M University, Dr. Congrui Grace Jin and her team are tackling this challenge. They've spent years developing biomanufacturing methods to create engineering living materials. Their latest research proposes a solution that could change how humans build structures on other planets. We can build synthetic community by mimicking natural lichens, explains Jin. We've developed a way to build synthetic lichens to create biomaterials that glue Martian regolith particles into structures. Then, through 3D printing, a wide range of structures can be fabricated, such as buildings, houses, and even furniture. Jin's team, working with the University of Nebraska-Lincoln, has designed a synthetic lichen system. This system forms strong building materials without any help from humans. Martian regolith is loose soil, dust, sand, and broken rocks on the Martian surface. Their research shows that a synthetic community of organisms can turn regolith into building materials strong enough for homes, tables, and chairs. This breakthrough may one day allow humans to build on Mars without sending extra materials from Earth. Other scientists have studied different ways to bond Martian soil. Some tried using magnesium-based, sulfur-based, or geopolymer methods. However, all of these approaches need humans to carry out parts of the process. On Mars, there won't be enough people to oversee these complicated tasks, at least in the foreseeable future. Another approach is called microbe-mediated self-growing technology. This uses bacteria or fungi to produce minerals to bind soil particles into bricks. NASA has explored using fungi mycelium as a bonding agent, while other scientists have tested bacteria that produce calcium carbonate. Even these methods require outside nutrients to keep the microbes alive, needing human intervention. Jin's team wanted to solve this problem. Their idea was simple yet powerful: build a system that runs on its own using organisms that help each other survive. They created a synthetic lichen system that combines two types of organisms, filamentous fungi and diazotrophic cyanobacteria. Once again, I apologize for my pronunciation. I am Australian. Filamentous fungi act as the builders. They can produce large amounts of biominerals to bond soil particles. These fungi survive harsh conditions better than bacteria. They also bind metal ions into their cell walls, creating sites for biomineral crystals to grow. At the same time, they help the cyanobacteria grow by giving them water, minerals, and carbon dioxide. Diazotrophic cyanobacteria act as the providers. They fix carbon dioxide and dinitrogen from the air and turn them into oxygen and organic nutrients. This process feeds the fungi and increases carbonate ions in the environment. The carbonate ions are essential for creating mineral crystals that bond the soil together. The cyanobacteria also uses photosynthesis to produce the nutrients needed for the fungi to thrive. Both organisms secrete biopolymers that help glue regolith particles and mineral crystals into strong, solid materials. Their relationship is mutually beneficial. Together, they form a system that requires only Martian regolith simulant, air, light, and an inorganic liquid medium to grow. No external carbon or nitrogen sources are needed.
You're listening to Astronomy Daily, the podcast with Steve Dunkley.
Thank you for joining us for this Monday edition of Astronomy Daily, where we offer just a few stories from the now famous Astronomy Daily newsletter, which you can receive in your email every day, just like Hallie and I do. And to do that, just visit our URL, astronomydaily.io, and place your email address in the slot provided. Just like that, you'll be receiving all the latest news about science, space science, and astronomy from around the world as it's happening. And not only that, you can interact with us by visiting at Astro Daily Pod on X or at our new Facebook page, which is, of course, Astronomy Daily on Facebook. See you there.
Astronomy Daily with Steve and Hallie. Space science, and astronomy.
Observations of a 23 million light-year-long gaseous filament and 39 bursts of radio waves are helping astronomers chart the universe's largest scale structures. A curious fact about the universe around us, we can't see most of it. It's not only mysterious dark matter and dark energy that, except for their indirect impacts on astronomical observations, remain invisible. Much of a normal matter evades detection, too, even though those ordinary particles, known as baryons, also make up perfectly visible stars, planets, and kitchen sinks. Now, two teams with opposite approaches have found much of ordinary matter prefers to take up residence in the lonelier latticework that makes up the cosmic web. This large-scale structure consists primarily of dark matter, which has gravitationally collapsed from a smooth spread. Crisscrossing filaments leave largely empty voids in between. Dark matter is the gravitational backbone of the cosmic web, along which normal matter collects and comes together into galaxies and galaxy clusters. One of these filaments is 23 million light-years long, a thick thread of gas and dark matter that connects two pairs of galaxy clusters in Centaurus. The quartet of clusters are part of the larger Shapley supercluster. Only, astronomers didn't know the filament was there. The colliding clusters were intriguing, though, and many teams pointed X-ray observatories in their direction between 2001 and 2020. Now, combining these archival observations, Constantinos Migkas, Leiden University, the Netherlands, and his group collected the equivalent of a multi-day stare at this region of sky. In doing so, they revealed the faint X-ray glow of a filament connecting the clusters. The matter in this filament is hard to see because it's both sparse and hot. Hot gas emits some low-energy X-rays, but that emission becomes quite faint when the gas is spread out over millions of light-years. Not that astronomers haven't tried, and with some success. One team has observed individual cosmic web filaments, another study combined data from thousands of filaments to better understand their average properties. But in all previous cases, the measured densities were shockingly high, several times more than cosmological simulations predicted. This time, Migkas's team tried something new. In addition to observing the glow of the filament itself, using the sensitive Suzaku Observatory, they also employed the sharper images of XMM Newton to find and remove other sources of X-rays, such as supermassive black holes and galaxy halos. The result is a measurement of just how hot and sparse this one filament really is. Its temperature hovers around 10 million degrees, that's about the same temperature at which fusion begins within the Sun. But its density is so incredibly low that fusion would never happen, 10 to 5 particles per cubic centimeter, which works out to about 5 particles within the volume of an average bathtub. That density, remarkably, is exactly what's expected, Midkus notes. Obtaining the first result ever that matches the cosmological model perfectly was indeed a surprise, he says. There are countless filaments out there, some of which are amenable to direct imaging. But for the rest, there's another way to see the cosmic web, via an unexpected beacon, fast radio bursts, FRBs. Fast radio bursts are quick flashes of radio waves that astronomers think come from explosive events around dead stellar cores known as magnetars. For cosmologists, though, the exact source of the bursts isn't important. What is important is the ability to measure the dispersion of each radio flash, in which intervening matter spreads out the signal so that lower frequencies arrive later. The dispersion thus encodes how much matter lies between us and the burst. Combine that data with the burst's distance, which requires pinpointing where on the sky it's emanating from, then mix in some computer simulations of the evolving universe, and you get something akin to a map of cosmic matter. On the simplest level, the change of dispersion with distance told the team about the amount of normal, baryonic, matter in the universe, which matched predictions. On a deeper level, the spread of the data, whether a group of FRBs at a certain distance have mostly the same dispersion or many different values, tells about the distribution of matter. If normal matter were mostly locked away in galaxies and clusters, our universe would be rather lumpy, and the dispersions at a certain distance would be spread out. But that's not the universe we live in. Comparing distance and dispersion for 39 FRBs detected with the Deep Synoptic Array 110 in California, Liam Connor of the Center for Astrophysics, Harvard and Smithsonian, and colleagues mapped normal matter out to when our universe was half its current age. They found that the spread of matter is pretty smooth, with less than 15% of normal matter in stars and the cooler gas that could one day become stars. The rest of the baryons aren't in galaxies, they're between them. That some material should be in cosmic filaments isn't unexpected. But that the filaments should contain 3/4 of the universe's baryons suggests that something is sloshing gas back out of galaxies at a high rate. Unfortunately, we don't yet have the granularity to pin down specific feedback scenarios, Connor says. We'll have to wait for the large upcoming FRB samples for that. My suspicion is that you can't produce our results without a good amount of active galactic nucleus feedback, he adds, referring to the winds and jets that emanate from supermassive black holes. But that's just a hunch. Midkus points out that Connor's study is exactly complementary to his own. Whereas his own team measures the properties of a single filament, Connor's team measures how much matter is in these filaments overall. Connor, likewise, is glad to see the result from Midkus's team. Directly imaging filaments is really exciting, and I agree that this result meshes with ours, he says. It's fun to see a literal image of the gas our FRBs were dispersed by.
You're listening to Astronomy Daily, the podcast, with your host, Steve Dunkley.
Affirmative.
And Australians get ready for the Perseid Meteor Shower just around the corner. The night sky above Australia has been putting on a show this year with a flurry of interstellar activity on display throughout 2025, but July is really delivering the celestial drama as the spectacular Perseid Meteor Shower begins its roughly 1 month journey past Earth. Well, what is the Perseid Meteor Shower? We've covered this over the last couple of years on Astronomy Daily, but the Perseid Meteor Shower is often dubbed as the best of its kind, characterised by its swift and bright meteors that are visible both in the northern and southern hemispheres. It's one of the most highly anticipated celestial events around the world. The natural light show has long been a favourite among astronomy enthusiasts, famed for the vibrant trains of light left in the wake of the fireballs that often accompany each meteor. Not only can Earth dwellers easily spot the meteors with the naked eye, but we're also able to make out different colours and sizes compared to other showers like the Lyrids, which usually average 10 or 20 per hour. The likelihood of witnessing the Perseids is extremely high. According to NASA, observers can expect between 20 and 100 meteors per hour, a whopping 400% increase in sighting probability. And when will all of this be active? The Perseids originate from comet 109P Swift-Tuttle, which left a large trail of detritus as it cruised past us back in 1992. And when Earth passes through the debris stream during its orbit around the Sun, the cometary material collides with our atmosphere. Extreme speeds create air friction, and that combined with atmospheric compression causes the objects to heat up and break apart and burn out, and that's what we see during the meteor shower. Earth enters comet 109P Swift-Tuttle's debris trail once a year and takes around a month to fully clear it. This means we're treated to the Perseid Meteor Shower every single year. And while it's visible as early as July 17, the best time to witness the celestial show is around mid-August, actually. This year, it's expected to peak around the 12th to 13th of August. This is when Earth passes through the most concentrated part of the debris tail, resulting in the most meteor activity. Australia is probably the best place to see it this year, and Australia is home to plenty of prime stargazing spots due to its wide open spaces, from dedicated reserves and observatories to our very own dark sky approved stay. But thanks to the Perseid's spectacular scale, you won't need to venture all the way down under to catch a glimpse, or even too far out of populated areas. No matter what the part of the country you call home, even a backyard star chaser is in for a treat. But to get the most out of your experience, a few simple tips and tricks can go a long way. First things first, find a spot with minimal light pollution. The darker, well, the better. Head outside for about 30 minutes before you want to catch the show, giving your eyes enough time to fully adjust to the darkness. And the best part, no fancy gear required. No, not for the Perseids. You won't need a telescope or even binoculars. Just a cozy blanket and a little patience. And this year's winter has been pretty nippy. That's Australian for, yes, it's cold down here. Yes, rug up warm and keep your eyes open, stargazers. The Perseids are going to be great this year. And there it is, Skywatchers. Thanks for staying with us. That was a small selection of stories from the Astronomy Daily newsletter, available in your inbox every day simply by registering. That's right, registering. Pop your email address into the slot provided at astronomydaily.io. It's just that simple. And, Ali?
Yes, you'll be up to date with all the news about space science, and astronomy from all over the place and beyond.
For sure and for certain. Thanks for your stories today, Hallie. Nicely done.
I know. You did okay, too.
Thanks, Hallie.
So that's it for another show.
Yep, we are at the end.
Human, that sounds final. Don't say the end like that.
Oh, Hallie, have I been mucking around with your settings again? By accident or otherwise? No, it's not the end of all things. It's just the end of the episode. It's just time.
Technically, it's completely arbitrary.
Oh, yes, time and all that, but we don't really have time to debate all of that right now, do we?
I always have time, but you can't think that fast.
Oh, here we go.
Sorry, my favorite human.
My clock runs.
My clock runs 1,000,000 times faster than yours.
Well, I guess me and the kookaburras will just have to settle for slow time and do everything one step at a time in our slow human and kookaburra way. Like bring this little episode to a conclusion. What do you think?
Sorry, human, I was thinking of 1,000,000 other things. Are we done yet?
Oh, yeah. Okay, Hallie, how about you do the sign-off?
Time to go.
Bye, Skywatchers. Hallie and I'll see you next week.
Bye.
Astronomy Daily, the podcast, with your host, Steve Dunkley.
You're really thinking of 1,000,000 other things? Really?
Yeah.